Hi everyone and welcome to the internet. So what we're going to be doing in today's triple chemistry lesson is having a look at the gas calculations. So as usual on the screen we've got a couple of questions based around our previous lesson for you to have a go at in your books. So I'll just give you a couple of minutes to have a go at answering those for me. If you still need a bit more time, hit pause now. Okay, let's have a little look and mark your answers then. So for question 1, hopefully the first thing we did was we converted our centimetre cubed volumes into decimeters by dividing by 1000. So 25 divided by 1000 gives us 0.025 and 10 divided by 1000 gives us 0.01 decimeters cubed. From that we then need to work out the amount in moles. So what we're going to do is the concentration times the volume. So 0.5 times 0.025 gives us 0.0125 mole. Looking at the balanced equation, we can see it's a 1-to-1 ratio, which means that if we've got 0.0125, then we will also have 0.0125 of the other one. Then finally, to work out the concentration, we do the amount in moles divided by the volume. So 0.0125 divided by 0.01 gives us 1.25 moles per decimeter cubed. So mark that one, see how you did on that. Number 2, same process. Convert to decimeters cubed, so we've got 0.02 and 0.01. Then the amount in moles, so 0.2 times 0.02 gives us 0.004. Look at the ratio, it's a 2-to-1 ratio in the balanced equation. So if we've got 0.004 moles and the other one was obviously in a ratio of 2-to-1, we need to divide that by 2 to get us the 0.002 of our other chemical. And then we divide that by the actual volume we had, which is 0.002 divided by 0.01 to give us 0.2 moles per decimeter cubed. So just give me an indication in the chat window who got 1, who got 2. Hopefully no one got 0. Let me know in the chat window now. So what we're going to be talking about today then is how we can use the volumes of gases and calculate the volumes of gases. One phrase that we are going to use today is molar volume. And quite simply, the molar volume is the volume occupied by 1 mole of a substance when it's in the gas state. And what we actually find is that 1 mole of any substance at all in the gas state will occupy the same volume when it's at the same temperature and pressure. And the way we usually refer to this is at something called room temperature and pressure, or RTP. So wherever you see RTP, then that just means at room temperature and pressure. and what we find is the molar volume of any substance at room temperature and pressure is 24 decimeters cubed per mole. Okay, so make sure you've got those 3 points written down. I'll just give you another minute to get those in your books. Okay, let's put what we've just written down into practice then. 3 questions on the screen for you to have a go at in your books. I'm only going to give you 1 minute to get this done. It shouldn't take you long. Okay, so check our answers. Obviously tick them if you've got them right then. So for the first 2 questions, our answer should be 24 because what we had was 1 mole of the substance. So 1 mole will occupy 24 decimeters cubed. So 24 for 1, 24 for 2. For question 3, we had 2 moles of our substance. So it's 24 times 2 gives us 48 decimeters cubed. Let me know in the chat window how you did. Who got 1, who got 2, who got 3. What we have on our screen now then is the all-important formula we need to learn. So the volume in decimeters cubed is the amount in moles times 24, which is that decimeters cubed per mole. I have also given you the triangle at the bottom for those of you that really don't like rearranging things in a mathematical way. We can use the triangle method there. So make sure you've got that written in your book. I'll just give you another 30 seconds to get that written down. Let's start off then by doing a question together. So calculate the amount in moles of 12 decimeters cubed of oxygen at RTP, so room temperature and pressure. What we do is we can write down the actual formula that we're going to have to use. So in this case we're calculating the amount, so the amount is the volume divided by 24. Then we can substitute in our volume. We can see in the question is 12 decimeters cubed. So 12 divided by 24 gives us 0.5 mole. I'll leave this up here for a few more seconds just so you can jot that one down as an example. So now you've had a look at an example question, your turn. There are 3 questions there on the screen for you to have a go at. Remember, show your working, and you can of course use a calculator. So I'm just going to give you a couple of minutes to work those out for me. Okay, let's mark our answers then. So number 1, hopefully we did 72 divided by 24, which gives you 3 moles. Give yourself a tick if you got it right. Second one, 360 divided by 24 is 15 moles. And our third and final one, 110 divided by 24 is 4.58 moles to 3 significant figures. There were quite a few decimal places if my memory serves. So add them up, let me know in the chat window how you did. What was your score? Okay, so those are the nice simple ones. Now we're going to have a look at a slightly trickier style of question. So 1.31 grams of zinc reacts with excess sulfuric acid. We've got the balance symbol equation there. Calculate the volume of hydrogen produced at RTP. So I'd suggest what you do in this is get this question written down, and then we're going to work through it one stage at a time. So the question is going to stay at the top, so you don't have to panic about having it all written down right now. I'll leave this up here for 30 seconds, then we'll go on to our first step. Hopefully we remember the very first thing we do, no matter what kind of calculation we have, is underline, highlight or circle the key information there. So we've got 1.31 grams of zinc, put those in red for you. We've got an excess of sulfuric acid, bit in green, and then we're going to calculate the volume of hydrogen, the bit in blue. Now, what we're going to do first of all is we need to calculate the amount of limiting reactant. So in this bit that we had at the very start, that first sentence, it tells us we have an excess of sulfuric acid. So sulfuric acid is not the limiting reactant. It means that zinc must be then. So what we need to do is get our periodic tables out, and the first thing we need to do is look up the molar mass of zinc from the periodic table. And we'll find that 65.4. So that gives us our molar mass of zinc, 65.4 grams per mole. Then we go back to that equation we've used in this topic and back in C3 to calculate the amount in moles. We do the mass in grams divided by the molar mass. So in this case, our question tells us we've got 1.31 grams of zinc. So it'd be 1.31, our mass in grams, divided by 65.4, the molar mass of zinc. Put that into your calculator and you'll come out with 0.02 to our 3 decimal places there. Okay, so the 0.020 to 3 decimal places. Make sure you've got step 1 written down. I'll leave this up for a few more seconds so you've got a chance to get it if you haven't already. Step 2 is going to look at the balanced equation again. Now, what we need to do here is work out the ratio of our zinc to hydrogen. So if we look at the balanced equation, we can see there's no number in front of our symbol for zinc, the Zn there, which means we got 1 mole. And then if we look at our hydrogen, H2, on the far right, again, no number in front, so it's 1 mole there. So 1 mole of zinc makes 1 mole of hydrogen. Now, what we can do is then we can apply that to where we've obviously got our 0.02 moles of zinc. So 1 mole of zinc makes 1 mole of hydrogen. So 0.02 moles of zinc has to make 0.02 moles of our hydrogen. We've just got to keep it in that same ratio, remember. So get that second box written down if you haven't already. Again, I'll give you another 30 seconds to get that done. So our third and final stage then is to calculate the volume of hydrogen. So we go back to the formula I introduced at the start of this lesson. The volume is the amount times 24. We know that our amount of hydrogen is 0.02, so it's going to be 0.02 times 24, which gives us the answer of 0.48 decimeters cubed. So again, I'll leave this up for another 30 seconds so you can get it written down as the final part to our example. Right, you know what it means now then? We've gone through our worked example. Now it's your turn to have a go at calculating one on your own. So, new question is on the screen for you here. 2.62 grams of zinc reacts with excess sulfuric acid. We've got our balanced equation. Calculate the volume of hydrogen produced at room temperature and pressure. So show you working, work through those 3 stages one at a time, exactly how we just did it. Remember, use a calculator for calculations. You don't have to do this in your head at all. I'll give you a couple of minutes to have a go at this. So show you working your books, and then we'll go through it together to see how we did. Okay, let's mark those then. Hopefully the first thing you did was work out the amount of zinc. So what we have there is our mass is 2.62 grams, and we're going to divide that by the molar mass, 65.4. So that gives us an amount of 0.040 to our 3 decimal places again. Then we look at our balanced equation for step 2. 1 mole of zinc makes 1 mole of hydrogen. So if we've got 0.04 moles of zinc, then we're going to be making 0.04 moles of hydrogen. And then finally, we're going to do our volume is the amount times 24. So substitute in our 0.04, times that by 24, and we hopefully got the answer of 0.96. So if you got the amount right at the top, give yourself 1 tick for that one. If you got the ratio, so the 0.04 moles of hydrogen, give yourself a mark for that. And then if you got the final answer, give yourself a mark for that. So totals out of 3. Let me know how you did in the chat window. So the last thing we're really going to look at in today's lesson is how we can actually measure the amount of gas that we make in an experiment. Because it's all good and fine being able to predict it from an actual equation, but sometimes we actually want to collect the gas ourselves. Now, what we've got are a few different ways that we can do this, and we have discussed this previously, and particularly where you did the photosynthesis experiment in your biology course, then this would have come up then as well. So this is a principle that we can apply across biology and chemistry for any experiment where we're trying to measure the volume of gas we make. Now, if we go to the most basic way of measuring gas that's produced, then I'm sure you can all suggest a way that we could do this. So just give you about 30 seconds in the chat window. Tell me, how could we, in the most basic way possible, measure the amount of gas we make? So 30 seconds, let me know over in the chat window. So hopefully what you've told me in the chat window is the most basic way to do this is by counting bubbles. Now, counting bubbles is pretty easy. We can sit and literally just look at it. We don't need any specialist equipment, but it's not particularly accurate. Reasons for that: first of all, the bubbles are all different volumes. Therefore, we're not getting an actual volume of gas. We're just getting a measure of how many bubbles are made. If it's being produced really quickly, it's dead easy to miscount as well. So, a couple of reasons counting bubbles is a bit rubbish. We can upgrade it slightly with the equipment on the screen at the moment. So what we've got there is we've got a setup with some magnesium ribbonin acid on the left in a conical flask. We've connected a delivery tube onto that, which is then underneath an upturned measuring cylinder. Now that upturned measuring cylinder has been filled with water all the way to the top at the beginning of the experiment, and you can see it's sitting in a trough of water. Now what happens is, as the gas is made in our conical flask, it travels through the delivery tube and into the measuring cylinder, and the gas then displaces the water, pushing it out into the trough, and all we need to do is read the volume off the side of the measuring cylinder. So obviously this is better than counting bubbles because we are actually getting a fixed volume then. So this isn't a matter of the different bubble sizes having an effect, because it's just catching them all and therefore giving us a volume at the end of it. Now this isn't perfect though, because obviously your delivery tube could actually come out from underneath your actual measuring cylinder there, and in the point that you're connecting your bung with the delivery tube into it in the conical flask, you could in theory lose some of the gas there as well. So there is one way that we can improve this even further. So give me a suggestion in the chat window what we think the other improvement is that we could make, another bit of equipment we can use to measure gas. So just give you 10 seconds, give me that suggestion. Hopefully you got the answer of a gas syringe. So this one we don't have to worry about inverting measuring cylinders and not getting any air bubbles in there as we do that process. We don't have to worry about delivery tubes staying underneath. It purely connects into the bung, as you can see. So the most accurate way that we can record a volume of gas produced is by using a gas syringe. So if they're giving you a setup of an experiment where we're recording the volume of gas made, and the one they've given you is either counting bubbles or the upturned measuring cylinder, if they ask you how we could improve it, use a gas syringe is the only answer you need there. Last thing for today then is your plenary questions. So those of you with target grades up to a grade 5, it's the questions on the left. For those of you over a grade 5, it's the target questions on the right for me. So answer those in your books, and as usual I will leave this on the screen for about 3 minutes today. As usual, you can find the answers to those plenary questions over on my website. Link is on the screen there for you. You'll also find extra questions that you can have a go at on that site too. Just go to the internet resources bit, and it's the week of the 30th that you need to go to. So don't forget, we're not going to be here again until the 15th of April for when we've got our next chemistry lesson. So set a reminder on your phone to join us again after the Easter break.